In the previous videos in this module, I've introduced you to the ideas of angular velocity and angular acceleration. In this video, I'm going to go through an overview of what we've already discussed regarding angular velocity and angular acceleration, and then we'll go to a quick example calculation involving angular acceleration. In the following videos, we will develop the tools we need for the more substantial computational problems. So first, let's remember what angular velocity is. The angular velocity is defined to be the rate at which the angular position of an object changes. When the angular velocity of an object is constant, we can then say that the angular velocity of the object is the change in the angular position of the object during some time interval divided by the time interval. Even when the angular velocity is not constant, we can still use the same formula, change in angle over change in time, to give us the average angular velocity during some process. As an example, here I've illustrated an object represented as a pink dot, which is moving around the circle, and I have shown where on the circle the object is at 1 second time intervals. So at time 0 seconds, the object is at the reference line here. At time 1 second, 30 degrees. At time 2 seconds, 60 degrees, and so forth. So let's say I'm going to act out the motion of the object. So at time 0 seconds, my finger would be here, and then time 1 second, times 2 seconds, times 3 seconds, 4 seconds, 5 seconds, 6 seconds. In that motion, did my finger have a constant angular velocity? An object has a constant angular velocity when the angular position changes by equal amounts in equal time intervals. In that motion, my finger moved through 30 degrees along the circle for every 1 second time interval. So 30 degrees in every 1 second time interval, I had a constant angular velocity. So what was that constant angular velocity? Well, if I move through 30 degrees every second, then my angular velocity would be 30 degrees per second. So the object, which is depicted here, had a constant angular velocity of 30 degrees per second. The other concept I wanted to quickly review here is the idea of angular acceleration. The angular acceleration is defined to be the rate of change of angular velocity. When the angular acceleration is constant, we can then say that the angular acceleration is equal to the change in angular velocity during some time interval divided by the time interval. To illustrate the idea of angular acceleration, look at the example motion that I've illustrated down here. So again, I have some object which is moving around the circle, and I've represented the object again with a pink dot. At time 0 seconds, the angular position is 0. At time 1 second, 30 degrees. At time 2 seconds, 90 degrees. At time 3 seconds, 180 degrees. So I'm going to act this out with my finger. 0 seconds, 1 second, 2 seconds, 3 seconds. So what was my angular acceleration for that motion? Well, let's work it out by finding the average angular velocity for each 1 second time interval. For that first 1 second time interval, from time 0 seconds to time 1 seconds, I went through 30 degrees in 1 second. So my average angular velocity for that motion would be 30 degrees per second. In the next 1 second time interval, I went through 60 degrees in that 1 second. So my average angular velocity for that time interval would be 60 degrees per second. And then in that last 1 second time intervals, I went through 90 degrees in 1 second. So my average angular velocity for that last second of motion would be 90 degrees per second. So I hope you see a pattern here. In the first second of motion, 30 degrees per second. In the next second of motion, 60 degrees per second. In the last second of motion, 90 degrees per second. Can you see that every second that went by, my angular velocity increased by 30 degrees per second? So what is my angular acceleration? Well, in a 1 second time interval, my angular velocity increases by 30 degrees per second. So for any of these 1 second processes, I could say that the change in angular velocity was 30 degrees per second, and the time interval was a second. So the angular acceleration would be 30 degrees per second squared. Now we're going to do a quick calculation, which I hope will get us a little further acquainted with the idea of angular acceleration. Here we have a child playing on a merry-go-round. The merry-go-round is going round and round counterclockwise at a constant angular velocity, and it is making one complete revolution every 3 seconds. Then the child decides that he wants to get off the merry-go-round. So to slow the merry-go-round down, he sticks his feet into the sand. And when he sticks his feet into the sand, the merry-go-round begins to gradually slow down. And 5 seconds later, the merry-go-round has come to a complete stop. For this process, we would like to find the angular acceleration of the merry-go-round in units of radians per second squared. And we're going to assume that the angular acceleration was constant during the process. So as I showed you before, when the angular acceleration is constant, we can take the angular acceleration to be change in angular velocity over change in time. When we do calculations involving rotational quantities, we have to define the positive direction for rotation. So here I have taken counterclockwise to be the positive direction for rotation, and I've indicated that by having an arrow here hooking in the counterclockwise direction with a little plus sign. And let's be clear that the merry-go-round itself also has a counterclockwise rotation when the process starts. Anyways, getting to the formula now, we have angular acceleration is change in angular velocity over time interval. Let's write change in angular velocity as the final angular velocity minus the initial angular velocity. Then we divide by the time interval. The final angular velocity is 0. I'll put that into the picture. The initial angular velocity is 1 revolution every 3 seconds. And we can write that, again, that should be in the picture. We can write that as a revolution every 3 seconds. So going back to the formula, we have angular acceleration is minus initial angular velocity, which is a revolution over 3 seconds. And then the time interval between the kid sticking his feet into the sand and the merry-go-round completely stopping was 5 seconds. Now notice if we were just going to do the calculation like this, we would have units of revolutions per second squared. But the problem is asking us for the answer in units of radians per second squared. So I'm going to use the conversion factor from revolutions to radians. So 1 revolution is 2 pi radians. So I can put in a conversion factor, 2 pi radians over revolutions. So revolutions cancels. So putting the numerical values into your calculator, minus 2 pi over 15 will give you minus 0.42, and then the unit will be radians per second squared. So now we've done a fairly straightforward calculation involving the angular acceleration. And in the next video, we're going to begin developing the tools we need to do more substantial problems involving rotational kinematics.